Good morning to all. Myself, Dr.Digambar M.Sapkal, Assistant Professor in Physics, SICS Degree College of Arts, Science and Commerce, Ambernath. Students, today we are going to see the theory, basic theory about the semiconductor diode. We know we are living in the semiconductor era. All the electronic devices and components, they are built up by using a semiconductor. By using these semiconductors, the first, that is the PN junction diode, is fabricated in the year of 1874. In the today's lecture, the content: introduction of semiconductor, introduction of PN junction diode under forward bias, PN junction diode under reverse bias, current voltage characteristics of diode, and application of semiconductor diode. Now, the first we see what is semiconductor. Students, we know the materials classified on the basis of energy gap between the valence band and the conduction band. The valence band holds the valence electrons while the conduction band is empty. The conduction occurs when the electron jumps from the valence band to the conduction band across the forbidden energy gap. Wider the gap between the valence and conduction band means more energy is needed to transfer the electrons from the valence band to the conduction band. We know there are three types of materials: conductors, insulators and semiconductors. They are based on this energy gap. The conductors have no energy gap because these bands are overlapped, and the electrons are easily move from the valence to the conduction band. The examples of conductors, they like silver, copper and aluminum, etc. The second type of material is the insulator, having a large energy gap, making conduction difficult. Insulators need a lot of energy to move the electrons from the valence to the conduction band and making them poor conductors. For example, mica, ceramic are common insulators. The third type of material is the semiconductor. It is a material having an energy gap between the conductors and insulators, and the gap is typically more or less 1 electron volt, and thus 1 electron requires more energy that insulating material for shifting the valence band to the conduction band. In this semiconductor, what is semiconductor? As we see the three different types of materials, that is the conductors, insulators and semiconductors. The semiconductor material is neither insulator nor conductor and having an energy gap about the 1 electron volt are called the semiconductors. Most common materials commercially used as a semiconductors is a germanium and silicon, because their property to withstand high temperature. That means there will be no significant change in energy gap with changing temperature, and that's why these two materials are used commercially. And the energy gap for the silicon is the 1.1 electron volt and germanium is the 0.72 electron volt. At room temperature, resistivity of semiconductor is in between insulator and conductor, and therefore semiconductors show the negative temperature coefficient of resistivity, NTC. That means the resistance decreases with increase in temperature. Both silicon and germanium are elements of fourth group, that is both elements have 4 valence electrons, both form the covalent bond with the neighboring atom, at absolute zero temperature both behaves like an insulator. The valence band and the conduction band is empty, but as the temperature is raised, more and more electrons are available at the conduction band. They transfer from the valence band to the conduction band. Now see the introduction of p-n junction diode. There is no doubt that semiconductor changed the world behind anything that could have been imagined before then. People have probably always needed to communicate and process data. It is thanks to the semiconductors that these two important tasks have become easy and take up infinitely less time. In the year of 1875, German physicist Carl Ferdinand Baron discovered and documented the first semiconductor diode effect. Baron observed current flows freely in only one direction at the contact between a metal point and the gallium crystal. And in the year of 1901, the first semiconductor called cat whiskers was patented. Now, semiconductor diode. What is semiconductor diode? Semiconductor diode is a p-n junction. It has a two-terminal device that conducts current in only one direction. This figure shows p-n junction diode. This is the p-type material, and this is the n-type material. These two materials are sandwiched together. These form the depletion region. And this is the schematic symbol of the p-n junction diode. This first terminal is called as the anode, second is called as the cathode. By applying the external voltage V, we can vary the potential barrier. Now this figure shows the p-n junction diode under forward bias. What is the forward bias? If the positive terminal of the battery is connected to the p-type and the negative terminal of battery is connected to the n-type semiconductor material, and this condition is called as the forward biasing condition. In the forward bias, the applied voltage essentially narrows the depletion zone, and it lowers the barrier potential, allowing charge carriers to cross the junction. As a result, electrons can move from the n-type material to the p-type material, and holes can move in the opposite directions, allowing electric current to flow through the device. This is called a forward bias of the p-n junction diode. Now, what is the effect of forward biasing? In the forward bias junction, what happens? The number of electrons and holes combine with each other after they cross the junction potential. In order, every holes of the p junction will combine with an electron from the n junction. This results in the breakage of covalent bonds and the current flow from p-type to n-type semi. Now, this number of electrons holes pairs are formed due to the forward biasing. The p region and the holes are the current carriers in the n region is electrons. It means in the p region the holes are the current carriers, and in the n region the electrons are the current carriers. Now what happens? Due to the forward biasing, the conductivity is increases. This is the second effect under the forward bias. Next, due to the forward bias, there is the reduction in the barrier potential also. Due to the forward biasing, there is a low resistance. Means diode exhibits the low resistance, allowing the efficient conduction of current. And due to the forward biasing, the forward voltage drop Vf is the voltage at which the diode starts conducting significantly. This voltage varies depending on the type of the diode. For example, silicon diode typically have a forward voltage drop around 0.7 volt. Now this is the forward biasing of the p-n junction diode. In case of the reverse bias, we see from this figure the negative terminal of battery is connected to the p-type region and positive terminal of battery is connected to the n-type region. When we apply the forward this reverse voltage, what happens? The semiconductor diode, when it conducts under the reverse bias condition, what happens? The negative terminal of the battery is connected to the P side, a P-type semiconductor, and the positive terminal is connected to the N side or the N-type semiconductor. When the voltage is applied across the diode, as the direction of the external voltage is same as that of the barrier potential, and therefore the voltage barrier sums up V0 plus V, and the width of the depletion region increases. In case of the forward bias, what happens? The width of the barrier potential decreases, and here in case of the reverse bias, the width of the barrier potential is increases, and as a result the motion of the carriers from one side of the junction to the another side of the another side is decreases significantly. This is the IV characteristics. See the current versus voltage characteristics of the diode. In the first quadrant, we see this is the forward region. Here the external battery, the positive terminal is connected to the P-type semiconductor, and the negative terminal of the battery is connected to the P-type. Here we observe that after a certain voltage, this is called as the knee voltage, what happens? Current is sharply increases. Clear? In the third quadrant, we observe the reverse bias characteristics. Under the reverse bias condition, what happens? As the reverse voltage increases, current is slowly increases. But after a breakdown voltage, what happens? Current sharply increases, and voltage approximately nearly same. This is the IV current versus voltage characteristics of the semiconductor diode. Now we come to the last slide. That is what is the application of semiconductor diode. It is used as a rectification of the alternating current. The Zener diodes are used for the stabilization of current and voltage in electronic systems. Photodiode works as a photodetector. And the next application, that is the switching diode, which is used for the fast switching requirement. The tunnel diode is also used as a special diode that is used in the negative dynamic resistance region. Next application of diode, it is LED, light emitting diode, is used for emitting an infrared light spectrum. And another application, that is the variable capacitance diode, is used when the voltage is applied in this condition. This is the basic theory of the diode. In the next part, we see the detail of the semiconductor diode again. We can stop here. Thank you for your patience. Thank you.